Picture this: scientists gazing at the infinite abyss, decoding the cryptic cosmic patterns that sprawl across the universe. They claim to have discovered enormous structures, vast beyond comprehension, billions of light years in size. Structures that push the boundaries of our understanding of the universe, like the Big Ring and the Hercules Corona Borealis Great Wall. But wait, there's a catch. Many astrophysicists remain skeptical, doubting these claims and pointing towards our own observational biases. These biases cloud our vision, you see. We are more likely to notice the brightest and the nearest celestial bodies, distorting our perception of the universe's large-scale structure. To counter this, scientists are trying to map out the universe in as comprehensive a way as possible, but the challenges mount up. Gravitational influences, the distribution of dark matter, and the inherent limitations of our observation methods. And then there are these supposed giant structures, the closed Campusano LQG, the giant arc. Are they real, connected structures? Or are they simply unrelated points that we, in our desperate need to find patterns, connect together? The debate rages on. The existence of these colossal structures in the universe is still up for grabs, but something you wouldn't believe is... we'll get to that soon enough. What's up, my incredible and curious folks? Ready to dive deep into the mysteries of the universe together? I'm your host, Chizar, and here with me, as always, is the insightful Sonia. We are here to ignite your curiosity on the Curiosity Wonderland.
Hey everyone, ready to get your minds blown?
That's the spirit, Sonia. Before we dive in, don't forget to subscribe to our channel and hit that bell icon so you never miss an episode of our cosmic voyage. And as always, get ready to have your minds expanded. This is the Curiosity Wonderland. Now, to understand the size of the largest structure in the universe, we need to picture the universe as a kind of cosmic web. It's filled with radiation, normal matter, and dark energy. And where these elements intersect, we find massive galaxies and galaxy clusters. But we also have great cosmic voids, areas with fewer galaxies and matter. We expect to see structures as large as 1 to 2 billion light-years, and voids as large as 3 to 4 billion light-years across. But beyond that, the universe should appear relatively uniform.
Wait. So you're telling me that the universe is like a huge cosmic web filled with clusters of galaxies and huge voids?
Exactly. But here is where it gets interesting. There have been claims of a giant, ring-like structure some 1.3 billion light-years across and 4 billion light-years in circumference. This structure, known as the Big Ring, is one of 7 claimed structures, which also include the Hercules Corona Borealis Great Wall and the original Klaus Campusano LQG from all the way back in 1991.
Hold up, these structures are supposedly billions of light-years in size?
Yes, they range from around 2 billion to 10 billion light-years in size. But here's the catch. While the scientists involved express little skepticism and point to statistical tests favoring their existence, the majority of the astrophysics community remains unconvinced.
So it's like the universe is throwing us a curveball.
That's a good way to put it. And it gets even more complicated when we consider that the galaxies and gas, which emit and absorb light, are not perfect tracers of the universe's underlying mass distribution, which includes dark matter. So, like any good mystery, it seems the more we learn, the more questions we have. And this universe mystery we're talking about, it's like trying to map out a terrain in the dark. The maps we create of the universe are fundamentally limited by the capabilities of our tools and the time frame of our observations. There's an inherent bias in these observations, known as Malmquist bias. We most easily see the things that appear brightest to our tools. Remember that evening when we tried to stargaze in the city and we could only see the brightest stars?
Oh, absolutely. I had a similar experience just last week. I was out in the countryside and the sky was filled with stars. But when I looked at my photos, only the brightest stars had been captured.
Exactly. And that's just within our own galaxy. Now imagine trying to map out the entire universe's structure. It's a challenge to do it without succumbing to the biases inherent in having a limited amount of data. The ideal would be to measure as much of the sky in as comprehensive a set of wavelengths and as deeply and faintly as possible. But even with this approach, there are still issues to be tackled. It's like trying to take a picture of every single star in the sky, near and far, with a basic camera. Now there's another fascinating aspect of this. When we observe a distant galaxy, we measure the light from it and how that light is redshifted or stretched by the expansion of the universe. But here's the snag. Galaxies also have their light get redshifted or blue shifted by the gravitational pull of nearby objects. This can throw off our inferred distance to them by up to a couple of 100 million light years. So, we need to correct for these gravitational influences, which presents its own set of challenges.
It's like the universe is playing an optical illusion on us.
That's a great analogy. Now, add to that the fact that we're not capable of making a comprehensive mass map of the universe through this method. We can only map out where the starlight, the stuff visible through our telescopes, comes from. To create a truly thorough map, we would need to construct a comprehensive three-dimensional lensing map of the universe, which is currently beyond our capabilities.
So we're still at the mercy of our own limitations and the universe's tricks.
It seems so. All of this makes you wonder, doesn't it? Just how much more is out there that we haven't discovered yet because we're limited by our current technology and understanding. And how will these discoveries change our picture of the universe? It's a humbling thought. What about you, dear listeners? Does this peek into the cosmic world excite your curiosity as much as it does mine? I would love to know. Don't forget to share your thoughts with us. Now, over the past 40 years, we've found lots and lots of structures in the universe ranging from a few 100 million light years up to about 1.4 billion light years in physical extent. However, while some of these are actually gravitationally bound structures, the largest of them, including our local supercluster, Laniakea, were formed by gravity and the evolution of the universe, but aren't actual structures. They are pseudostructures, made of separate bound clumps of matter that will forever be driven away from each other due to the presence of dark energy.
Wait a minute, so you're saying that our minds might sometimes trick us into seeing structures where there are actually none?
Exactly. The human tendency to connect the dots wherever we see adjacent points of light near each other can sometimes lead us to declare that we've found a structure when what we've found might just be a pseudostructure, an association, or even non-existent patterns in the noise.
But then, how do we differentiate between an actual structure and a pseudostructure?
Well, we have to keep our minds open to the possibility that there really could be larger structures than we expect. However, any assertion of structures so large that they shouldn't exist should be taken very seriously. We need a demonstration that these are real structures, not just apparent associations.
So it's not just about seeing it, but also proving it, right?
Absolutely. It's also about exploring the universe in new ways, like using X-ray and radio data to search for active black holes, using the 21-centimeter emission line from hydrogen to identify current or recent star-forming regions in galaxies, or using absorption features such as those from neutral hydrogen to identify intervening clouds of matter. Now, there are some intriguing methods to observe the universe, which include looking for quasars and gamma-ray bursts. Quasars are the brightest class of supermassive black holes, typically caused by normal matter falling into a supermassive black hole, heating up, and emitting radiation across the electromagnetic spectrum. As for gamma-ray bursts, they are extremely energetic stellar cataclysms arising from supernovae and neutron star collisions, among other events that last anywhere from just a few milliseconds to many hours.
Can you give us an example of a gamma-ray burst?
Certainly. On August 17, 2017, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves from a neutron star collision. Within 12 hours, observatories had identified the source of the event within the galaxy NGC 4993 and located an associated stellar cataclysm called a kilonova, caused by the collision of two neutron stars.
And what about quasars? Could you give us an example of these supermassive black holes?
Well, finding quasars is a bit more tricky. Most galaxies do not have a quasar at their core. quasars often result from the mergers of massive galaxies, but they're relatively rare. The first identified grouping of objects that appeared to violate the cosmological principle was the Claus-Campusano LQG, found in 1991. This grouping of 34 quasars, however, could just be 34 random points that are not part of the same structure.
So we're still figuring out the intricacies of these celestial bodies.
Absolutely. We're constantly learning and unlearning as we delve deeper into the mysteries of the universe. Now, the giant arc and the Big Ring, two of the newest structures we've identified, were found by connecting nearby points using absorption features.
Absorption features? Could you clarify that a bit?
Absolutely. These points were identified by the signature of singly ionized magnesium, a feature that can be mapped by looking at the absorption features of background quasars as their light passes through the intervening matter when it's been heated sufficiently, likely by a nearby star-forming region.
Interesting. So we're using quasars as cosmic flashlights to illuminate what's in front of them.
That's a great way to put it. They act as a backlight for the clouds of matter in front of them.
But isn't there a risk of bias in this approach?
Indeed, there is. It's like if you were mapping houses in the United States, but only looked at pink mansions. If you connected the dots, you might find what appeared to be a pattern to their locations, but it wouldn't represent the true distribution of houses in the US.
So we can't rely solely on these methods to map the universe?
Exactly. Maps of quasar groupings, gamma-ray bursts, or ionized magnesium absorption features aren't good proxies for the large-scale structure of the universe. These rare finds aren't indicative of the true distribution, and until we map that distribution, we have no reason to believe that these are real structures. Now consider the coathanger, also known as Brocchi's cluster. It's an asterism of 10 stars shaped like a coathanger. Many have called it a cluster in the past, but a close analysis shows that it really is a chance alignment of unrelated stars. These stars range from 235 to 1,735 light-years away, with no two stars closer than about 20 light-years to one another.
So it's not even a cluster. It's a perfect example of how looks can be deceiving, especially when it comes to celestial bodies.
That's right. There is actually a star cluster in that region of sky, but it's much farther away, between 4,000 and 5,000 light-years away, all unrelated to the foreground stars, which are all unrelated to one another.
So we can't just rely on our eyes or even basic statistical analyses to draw accurate conclusions about the structure of the universe.
Exactly. A visual inspection and a statistical analysis is no substitute for comprehensive data. For instance, there is an association of 9 gamma-ray bursts, all located around 9 billion light-years away. They were seen over a period of 8 years, from 2004 through 2012. Though we could be tempted to see a pattern or a connected structure, it remains unknown whether any two of them are even part of the same cosmic structure. So, where does all this leave us in terms of the giant arc, the Big Ring, and the other so-called cosmic structures that are allegedly too large to exist?
I guess it all boils down to the data, right?
Exactly. And being responsible about the science we're dealing with. Some might quickly conclude that these structures violate the cosmological principle, suggesting that our concordance model of the inflationary hot Big Bang with dark matter and dark energy dominating the universe must be wrong. They might even appeal to alternative, even non-viable models, and declare that all of modern cosmology's successes are irrelevant when considering these structures.
But that's jumping the gun, isn't it?
Absolutely. If we want to show that these are actual structures, we need to map out the full suite of matter and galaxies in this region and demonstrate that they're not just points in the cosmic web, but actual tracers of galactic filaments and genuine structure.
So it's a matter of gathering more comprehensive data and not relying solely on statistical tests and analyses.
Correct. The truth about these cosmic structures, like the truth about Brocchi's cluster or the underlying housing distribution based on pink mansions, cannot be determined by just statistical tests. It takes comprehensive quality data to determine whether a grouping or association is actually a real structure. Until that data arrives, we should all remain appropriately skeptical of claims that these so-called structures are anything more than coincidences. So, as we've discussed, the notion of gargantuan structures in the universe, such as the Big Ring and Hercules' Corona Borealis Great Wall, has been proposed. Yet, their existence challenges our current comprehension of the cosmos. The quest to verify their existence is hindered by biases in our observations, which lead to a skewed understanding of the large-scale structure of the universe.
And it's not as simple as just observing more. We need comprehensive, unbiased maps of the universe. We need to overcome the gravitational influence of nearby objects on the redshift of distant galaxies, and we need to map not just where starlight comes from, but the entire mass distribution of the universe.
Right. Until we have this comprehensive data, claims like the existence of structures like the Klaus-Campusano LQG and the giant arc remain speculative at best. It's like trying to find a whale in a bathtub, but all you have is a toothpick.
Haha, that's a great way to put it. And on that note, we'd like to thank all of you for joining us on this cosmic journey. If you enjoyed our dive into the mysteries of the universe, make sure to blast that like button, leave a comment, and share this episode with your friends.
We always appreciate your company on these celestial explorations. From the heart of the universe to the heart of the city, we're here, dedicated to unraveling the mysteries of the cosmos. Until the next time, goodbye and stay curious.
Yes, keep your eyes on the skies and your minds open. Goodbye, everyone.
I came across this fascinating insight on the Big Think site. The article titled "Giant Ring, Giant Arc, These Structures May Not Even Be Real" was penned by Ethan Siegel and published on January 23, 2024. If you're eager to explore further, you'll find the full URL in our video description. And now, I'm signing off.